Hello, and welcome to my Lab 4 video report where I'll observe the motion of a mass hanging from a spring that is moving along both the x and y direction. In this presentation, I'll review the fundamental principles and equations that are involved in this experiment. Then I'll analyze the motion of the mass hanging from the spring in Tracker. Then I will use VPython to model the motion of the object as well as graph the various energies such as the kinetic, potential, and total energies of the system. Then I'll discuss the what does it mean questions. And for my experiment, I found that the model somewhat fits the experimental data, the energy principle is indeed satisfied, and the periods on the x and y direction of motion differ greatly. These are the fundamental principles I have used. The first one I have used is Newton's second law, which states that the change in the net force is equal to the change in momentum over a change in time. The second fundamental principle I have used is the energy principle, which states that the total energy of the system is equal to the change in kinetic energy plus the change in gravitational potential energy plus the change in the spring potential energy. This is the motion of the mass I have analyzed in Tracker. The mass is hanging from a spring and is moving in both the horizontal and vertical directions. Before we can even model the motion of the object, we need to know properties of the spring itself. The spring constant can be calculated if we're given the mass of the object and the period of oscillation, using this formula right here. The relaxed spring length can be calculated by Hooke's law using this equation right here. In this case, the force is the weight of the object at equilibrium, K is the spring constant calculated here, and L is the length of the stretched spring at equilibrium. And equilibrium is when the mass is just hanging motionless from the spring. The period of oscillation can be calculated by finding the time intervals between two adjacent relative mins or maxes. Since this is 2D motion, where the system is moving both up and down and left and right, this should be done for both the x and y directions. Here is a section of a graph from Tracker. We take the first pair of mids and calculate the period, which is the time interval between when the system reaches the minimum position a second time since the first time. We do this for both the x and y values and then average the two periods to obtain a period that represents both the horizontal and vertical motion of the system. With the period, we can now calculate the spring constant. This right here is the equation that can be used to calculate the spring constant. We know what pi is. We're given the mass of the object hanging from the spring, which was given from the lecture video, and we calculated the period just earlier. So plugging these numbers right in, we get a spring constant of 6.96 newtons per meter. Now with the spring constant, we can calculate the relaxed spring length. The equation to calculate the relaxed spring length is Hooke's law, given right here. We calculated K earlier. We know what the mass of the hanging mass is, and we know what the acceleration due to gravity is, so we can calculate the net force acting on the spring. And this is at equilibrium, where the spring force equals to the weight force. And from the lecture video, we're given what the equilibrium length is. So plugging these numbers in and rearranging the equation, we get a relaxed length of 0.134 meters. Now we can model the motion of the mass. In this case, the system here is the hanging mass on the spring. Using Newton's second law and the position equation, the position of the mass can be tracked in the computer model. And this right here is Newton's second law rearranged. The net force is defined as the spring force plus the weight force, given right here. The spring and weight forces can be calculated below, where the spring force is calculated by Hooke's law, and the weight force is calculated by mass times gravity. During motion, the spring force is not equal to the weight force. In equilibrium they are, but when the object is moving around, then they are both not equal to each other. After computing the net force, the final velocity after a very short time interval on the system can be calculated using Newton's second law. Then the position of the mass can then be calculated using the position formula, with the approximation that V average equals to V final, since the net force is non-constant in this situation. After determining the new position, we compute the individual energies of the system. The energy principle is given as the total energy equals to the kinetic energy plus the gravitational potential energy plus the spring potential energy. The system in this case is chosen to be the mass and the spring and the earth so that there are no external inputs of work or energy into the system. All of the energy changes are within the system, but none goes in or out of the system. Therefore, the total energy change is zero, which is equal to the sum of the individual energies, and we're using the assumption that the spring is massless here. The individual energies can be calculated using these equations right here. As the energy principle and the choice of system mentions, the sum of all of these energy values must add up to zero. All these equations have to be calculated and recalculated after every time interval delta t so that the new energy and position values can be obtained. Since these calculations are tedious by hand, VPython will be used to model the motion of the spring iteratively. It will also generate a graph of the three individual energies so you can check if they all add up to zero. This is my computer model, which models the motion of the mass hanging from the spring. It seems like the model does a relatively okay job approximating the motion. When the motion of the mass is right over here at the high point, they both match pretty well. But when they go downwards, then the model and the actual motion differ greatly. This continues going on and on. This is the energy graph produced by VPython. There are some errors in this experiment when analyzing the motion. There's human error from tracker when we are tracking the motion at every frame of the video. There's a huge inconsistent X period as mentioned in the computer model. The period is not consistent because when it goes down the period is fast, but when the object goes back up the period is much slower. And the mass of the spring, as mentioned earlier, has been neglected, so that if it is actually not negligible, it will introduce some error into the calculation. So is the energy principle satisfied? Here's a legend of the various lines shown in the graph. The total energy is this yellow line, which lies around the x-axis, exactly at zero, with some minor deviations here and there due to errors in the experiment. So overall, yes, the energy principle has been satisfied. So how does the oscillation period vary in the x and y direction? Here's a table of oscillation periods with using the graph produced from tracker. The x graph has 5 periods and the y graph has 6 periods. And we can see that they differ pretty greatly, but look at the percent difference, which ranges from 0 to all the way up to 12%, mostly staying at around 12%. So yes, they differ pretty greatly. This concludes my lab report. Thanks for watching.